One of the pieces of information I want you to kind of take away from this is this weird understanding that if you take a spring and you were to stretch it, we know that you're doing work on the spring, but the spring is also doing work on you. And then we know that by stretching it, you're actually storing energy in the spring. You have a change in the potential energy in the spring. But the signs matter here, and let's see what we can come up with. So when we stretch the spring, we know that this is the stretch distance down here. This is x. This is the force here. Now, in this, the way you did in the lab, the structure worked out like this. This is the force that you applied, and this is the distance it stretched. So we know the work done here was this area. That was the definition. That's what we've been going with here. But what I notice is that the work done is the area, but we also use this as our same definition for this is also the change in this is elastic potential energy, the potential energy in the spring. If you started from 0, then it was just a change, but even if you looked at it from like here to here, right? You can see there's a change in potential energy there. But you pulled it and it stretched, and so we say the work is equal to the change in potential energy. But this is actually semantically true. Here's the difference though. This is the work done by you on the spring is equal to the change in the potential energy. But as you're doing work on the spring by stretching it out, the spring is actually doing work on you. And those two works, they're like Newton's third law force pairs, they actually have to be the same in value but opposite in sign. And so the work that you do on the spring is equal and opposite to the work that the spring does on you. Therefore, and this is the conclusion statement here, so this is the work done on the work you do on the spring, and this is the work you do on the spring. So the change in potential energy of the spring is equal to the negative of the work done by the spring. And this is a conclusion that's going to be important for us. This is going to be important for us. It's similar to the fact that this would be a y equals mx plus b, so this would be a positive slope, but the way that we see Hooke's law is the force by the spring vector is equal to k x vector, but it's negative because you stretch it, the stretch distance is one direction and the force by the spring is the opposite direction. So this negative sign here and this negative sign here are analogous. And we have a general rule for this because the definition for work is F dot D, where F and D are vectors, we're looking for the parts that are parallel to one another. So here's how the rule works. If the F and D vectors are in the same direction, if F and D are in the same direction, then the work is positive. And the converse is true. If you're in opposite direction, then your work value is negative. And this is going to be important for us to understand if you're storing potential energy or you're getting potential energy out of the system. And that's going to be important. Let me give you a gravitational example and you can see how you like it. We're going to consider a weird roller coaster that starts up here, dips down, up back a little bit, and ends down here. So we're going to put our roller coaster in a couple different locations, which we'll call A, B, C, and D. So here's our roller coaster up here to start. It's moving kind of slow. It's just going to roll over this first one. Down here it's moving faster than here. Slows a little bit going to the top of this hill. And then down here it's moving the fastest. And so we have a sense of how this works. Going slow, speeds up, slows down, speeds up a ton. And we can even look at what the energy bar charts for this look like at any given moment. In this, there are no springs, and let's assume for now it's frictionless. We have some gravitational potential and some kinetic energy. Gravitational potential energy and kinetic energy. And so let's look at them. Here, we'll call this down here. We'll let this down here be our h equals 0. We'll measure all our gravitational potentials up from there. So here it's the highest, it has the most gravitational potential. And it's moving slow, so it has a little bit of kinetic. When it gets to here, it's dropped about halfway down, so it has about half as much gravitational potential as it did there. And here it has a little bit of kinetic. Goes back up the hill, more gravitational potential than it did before. And then down here, it's all kinetic. And what we're noticing here is there's a change in the gravitational energy as it goes from each one. So let's see what happens from A to B. Okay, let's see what happens from A to B. We're talking about the gravitational energy here. So if you think about the gravitational energy, the gravitational potential energy, what's happening in this situation? Well, what I notice is that as it rolls from A to B, which way is the force? The force is in the down direction, and get this, so is the displacement. The distance is also in the down direction. And when the force and distance are in the same direction, we say that the work done is positive. Okay, the work done is positive, but because the work is the opposite, the negative work gives you the change in potential energy. What we notice here is even though the work is positive, we get a decrease in the kinetic energy. So from A to B, the force is down, the distance is down, the work is positive, but we have a decrease in potential energy, and that is consistent with this idea that the work is equal to the negative change. Let's look what happens from B to C. From B to C, the force is down, but the distance is up,
see you later.
All right, thanks. The force is down, but the distance is up. Therefore, we're going to have some negative work. Okay? So from B to C, the force is down, the distance is up, therefore the work is negative, but that results in an increase in the potential energy because, again, they're the opposite. So when the force and distance are in the same direction, we have positive work, but positive work that's negative gives you a decrease in kinetic energy, and we're in the opposite directions, right? You have a negative work, but negative work results in an increase in kinetic energy. Just like we did with the spring, right? Now, this was the force that you applied, but when we're talking about the spring, when the stretch distance and displacement are in opposite directions, you're storing energy in there. Just like we did here, when they're in opposite directions, you're actually storing more energy. And don't forget that this gravitational energy is stored in the gravitational field.